Hi, my name is Benjamin Osebonsu. I'm working with a wonderful partner. Please introduce yourself.
My name is Andre Pineda.
Yeah, I am a high school chemistry teacher. I teach in Baltimore, Maryland, specifically Cabo Voltaic High School, and I've been teaching for the past 12 years, heading to my 13th year. So I'm looking forward to coming school year.
Yeah, so I teach in the White River Indian Reservation here in Arizona, and I'm doing STEM at Kenyon Day Junior High School.
Awesome. So our topic is uh, based on redox reaction, powering batteries, and making battery connections and beyond. So basically, this is more like a high school chemistry lesson exploring reduction and oxidation reactions through like hands-on battery construction and sustainable energy applications. So the goal is to see how battery works, pretty much, and how we apply batteries in our everyday life. For batteries to work, we have a reaction called redox reaction. So how does redox reaction apply to most of these batteries that we see around us? All right. So I want us to acknowledge few people here and how batteries again are related in other careers. But firstly, again, we want to acknowledge Dr. John Allen, who's a senior scientist at the battery science branch in the U.S. Army Research Laboratory at the Delphi Laboratory Center, and also his co-mentor, Dr. Dat Tran, who's also the deputy chief at the battery science branch in the same location at the Delphi Laboratory Center. Both scientists are very, very unique in their research and they are very helpful. It was a pleasure working with them this summer in the lab and learning more about, their battery research. They have similar interests when it comes to research. They are both very interested in, materials like making materials that have low and high temperature. So if you have material, how well can it stand in a low temperature and how well can it stand in high temperature? They are both also interested in lighters and developing safer, long-lasting, fast-charging batteries. Hence, this pretty much presentation about redox reaction and battery making. So we all use batteries. At this point in our life, almost everybody use cell phone, and cell phone cannot operate without batteries. So batteries around us, from our car batteries to our cell phone batteries to the batteries in our remote control. Batteries are everywhere. So there's a huge, career connection with batteries. Chemists use batteries, biochemists use batteries, environmental scientists, chemical engineers, corrosion engineers. Batteries are used pretty much across the field. So I don't think there's any particular household in the country where you probably wouldn't find a battery. So battery is a big thing, and that's why we have this research and about batteries, and we want to acknowledge these wonderful scientists for opening up their doors for us to, learn more about batteries and our everyday life connection to it. So our focus on this lesson pretty much is to again know redox reaction, which has a huge connection to batteries. So you want to define what redox reaction is. You want to kind of like evaluate battery technology, how batteries impact our environment, and how can you make it sustainable. We want to also apply what you call oxidation numbers when it comes to these redox reactions and make sure that, we can develop or design a battery and know how, electrons and ions are moving between one area of the battery to the next. If you look at every battery, everybody have a positive and negative end. And so you want to make sure how does that work? Where did it come from? And see how all this apply in our real world applications. So there are several standards that this is based on, focusing on the next generation science standards and the ELA standards. So these are some few standards that connects to redox reaction and battery development. So we talk about energy and matter in the flow of systems, talk about the rate of reaction and chemical processes. All these are standards that are related to redox reaction and battery connections. There are several materials that we are hoping students will be able to know how to use in making batteries. So these are some of the few materials that, we hope students can do and use. But as you know, the lesson start is a very pretty much simple question to ask students: how does battery work? Like we said, battery is something that we all use every day. So to help start this lesson, we're hoping students can understand how battery works. You ask them question. They compare double A battery to maybe their smartphone battery. Like, everybody can like have a smartphone at some point or have come across a battery. So just try to get a prior knowledge out of them, see the understanding of battery. And so they'll have a think, talk, write action to help them discuss and share knowledge and the understanding of how batteries work. Then once they have, share out and discuss how batteries work, they will explore how batteries work. So in the exploration, they're going to kind of like build their own voltaic cell batteries. So as we said, for every battery, there's a positive side and negative side. The positive side in the voltaic cell is what you call the anode. And so the the positive side is the cathode and the negative side is the anode. So every battery you see is positive, negative, positive, negative. So negative is anode, positive is cathode. So students probably have seen this in their battery, but they may not have that, scientific understanding that that positive is cathode and that negative is anode. So as they build this voltaic cell, that help them to understand more about why these positive and negative are found in almost every battery around us. So after the exploration and after they build their own voltaic cell, they'll collect data, analyze the data, answer some concluding questions, and discuss it among themselves. We have some guiding questions to kind of like guide them so that they can use it to answer some questions and have a group and class discussion afterwards. So over to you, Andre.
Okay, so for the explanation part of this lesson plan, the students will review and deepen their understanding of the redox reaction by connecting their lab results to the oxidation numbers, half reactions, and electron transfer. And through this direct instruction practice and discussion, students will link their hands-on experience to scientific concepts and sustainable battery application. And for the elaborate part of this lesson plan, the students will extend their understanding by analyzing real-world battery designs and evaluating them for sustainability, safety, and redox efficiency. And working collaboratively, students will create posters or digital infographics comparing multiple battery types. And for the evaluation, students will demonstrate their understanding of the redox reactions, oxidation numbers, and sustainable battery design through a choice board exit ticket. So we do have three options. We have option one, problem-solving scenario, where students will analyze a real-world battery challenge, and they will identify redox pairs and predict how long a device can operate, justifying their reasoning using scientific concepts. Option two will be just a multiple choice questions. Students will answer 5 to 7 questions on oxidation numbers, redox agents, voltaic cell components, and sustainable battery advantages. And for the last option, students can choose this option and they will respond to the following in writing. They're going to describe 2 real-world situations where redox reactions are important besides batteries and explain why the redox model fits its case. Then I think that's it for our lesson plan.
So thank you very much for hearing us out. Hopefully you take a look at the main lesson plan, which will be attached to the video, and try it yourself. It is fun because batteries are everywhere. Thank you.
Okay, thank you.